Gravitational waves are extremely weak. These waves wouldn't be felt by a human, for example, or any other living creature for that matter. So in order to detect gravitational waves, scientists must use the most sensitive instruments ever invented. And what devices are suitable for measuring incredibly small changes? Well, lasers, of course. And that means we'll also need our good friend, the Michelson-Morley interferometer. Remember, interferometers leverage the wave nature of light to measure the difference in lengths between different beam paths. When coherent light, light that has the same phase, such as laser light, is split between two different paths and is later recombined, its brightness will depend on how different the two paths were. For example, if a red laser with a wavelength of 650 nanometers is introduced into an interferometer, it will produce a bright spot at the end of the detector if there's no difference in the beam path. If one of the arms differ in length by half of the red wavelength, or 325 nanometers, the interference between the two beams produces zero light. So small changes in the length of one arm of an interferometer can be measured by the changing brightness of the resulting pattern of light at the detector. The original Michelson-Morley interferometer was developed to determine if the flow of ether caused a delay in one of the device's two arms, instead of the difference in the arm's lengths. Like a boat traveling against the current of a river, the theory of light back then predicted that moving ether would cause a delay in the upstream arm. The opposite was discovered, that there was never any delay, no matter what the orientation of the device, with respect to the motion through the supposed ether. This proved that light waves don't require a medium like ether to travel in, and as a consequence, the speed of light is a constant. In order to leverage the sensitivity of interferometers, astronomers built the Laser Interferometer Gravitational Wave Observatory, whose acronym is LIGO, pronounced LIGO, or sometimes LIGO. These are two massively improved versions of the Michelson-Morley interferometer, built on either side of the continental United States. One detector is in Hanford, Washington, while the other is precisely 3,002 kilometers away in Livingston, Louisiana. They each have two arms, but instead of short meter-long arms like the original Michelson-Morley interferometer, each of the arms of LIGO is 4 kilometers long. In addition to the length, each arm bounces light from the laser source back and forth about 280 times, making each arm of LIGO equivalent to the length of 1,120 kilometers. Why are LIGO's arms so long? Well, it's hunting for some of the weakest signals that the universe has ever thrown at us. In fact, in order for LIGO to detect the strongest gravitational waves, it needs to be able to distinguish a change over the 4-kilometer length of its detector arms, a difference in length 1,000 times smaller than the radius of a proton. But one LIGO isn't enough to catch a gravitational wave. We need at least two. There are several major gravitational wave observatories in operation around the world. The two LIGO observatories were the first, followed by Virgo, and a host of others in operation and under construction around the world. If one LIGO detector is sensitive enough to measure a change in its arm length down to the level below the width of an atom, why make more? Well, the first and most important reason is noise. Yes, sounds, footsteps, earthquakes, and cosmic gravity quakes all register in LIGO as a change in the length of LIGO's arms. And in order to filter out footsteps from a colliding black hole, you need a second detector. LIGO's second detector, built in Livingston, Louisiana, has a different set of sounds, footsteps, and earthquakes. But presumably the two LIGO detectors would both see the same gravitational wave coming from an intergalactic source. To determine whether a wiggle in one LIGO detector is the result of a gravitational wave, scientists compare the data from the second. If there's a wiggle at nearly the same time, remember the detectors are separated by 3,002 kilometers, with nearly the same shape, scientists can be confident that they really saw a gravitational wave and not some researcher sneezing in the control room. But there's another important reason to have more than one gravitational observatory: direction. With only 2 LIGO detectors, an incoming gravitational wave will not have a well-defined direction. Just like having 2 ears gives us stereo hearing, 2 LIGOs let us determine approximately where the source is. Although with only 2, there's still uncertainty about which direction it came from. In order to pin down the source of gravitational waves, a 3rd gravitational observatory is necessary. In the case of the kilonova explosion resulting from the merger of 2 neutron stars in 2017, the gravitational wave signal was also detected by a 3rd gravitational wave observatory, Virgo, in Italy. With all 3 gravity wave observatories up and running, most major astrophysical mergers will be detected. Over the next few decades, these types of observatories will get more and more sophisticated, detecting dozens of compact object collisions in the universe. But things will get really interesting once we send these massive observatories into space. In order to really make the most sensitive gravitational wave observatories, scientists work hard to remove sources of error. Just like telescopes, which are better if they're on mountaintops, but best if they're in space, a space-based gravitational observatory wouldn't have to worry about earthquakes or someone tripping on a banana peel near the detector. No, the next generation of gravitational observatories will be built in space. The Laser Interferometer Space Observatory, whose acronym is LISA, universally pronounced as LISA, but I would argue it should be pronounced LISA in this case. LISA consists of 3 spacecraft, which will trail behind Earth in its orbit around the Sun, flying in a triangular formation. Each of LISA's arms extend between the 3 spacecrafts, and instead of a puny 1,120 kilometer effective arm length, LISA will have 3 2.5 million kilometer long arms. LISA will still be sensitive to small changes in the length between the arms, but will have an incredible sensitivity of 20 picometers over the 2.5 million kilometer long arms. As a result, LISA will be able to detect much smaller and quieter collisions than LIGO, but also begin probing into the processes by which compact objects are captured by, but not collided with black holes. Beyond LISA, which won't even launch until the early 2030s, future gravitational wave observatories will measure the rotation of compact objects like pulsars.